Welcome back to the series. In our last video, we covered the core concepts of machine learning: regression for predicting numbers, classification for predicting categories, and the fundamental learning process of minimizing a cost function using gradient descent. Today, we're going to put that all into practice and build our first true powerful classification model, logistic regression. This model is a cornerstone of machine learning, so we're going to give it the detail it deserves. Just to refresh, our goal with binary classification is to predict one of two outcomes: a yes or a no, a 1 or a 0. For example, is this email spam, class 1, or not spam, class 0? Will this customer churn, class 1, or not churn, class 0? The output we want is a simple, clear category. Now, your first instinct might be, hey, we learned how to make a line. Can't we just use that? And this is the critical first question. Why can't we just use linear regression? Well, look at this. Let's say we plot hours studied versus pass 1 or fail 0. The data is clustered at y equals 0 and y equals 1. If we try to fit a linear regression line to this, we get two massive problems. First, the line looks like a terrible fit. But second, and more importantly, the line predicts values we can't use. It predicts values like 1.5 or minus 0.5. What does a minus 50% chance of pass even mean? It's nonsense. We need a different approach. The solution is elegant. Instead of trying to predict 0 or 1 directly, let's have our model predict the probability that something is a 1. We need a model that always outputs a number between 0 and 1. For example, if we feed it an email, it might output $0.8. We can interpret that as an 80% chance of being spam. If it outputs 0.1, that's a 10% chance. This is a much more useful and logical output. But how do we force a model to only output numbers in this range? We do it with a magic mathematical tool called the Sigmoid Function, which is also why this is called logistic regression. Don't worry about the equation, just look at the shape. It's a beautiful S-curve. Look at the y-axis. No matter how large and positive the x value is, the output never goes above 1. And no matter how large and negative the x value is, the output never drops below 0. It perfectly squashes the entire number line into the 0 to 1 range. This is exactly what we need. Let's see this in action. If our model calculates a score of +8, we pass it through the sigmoid function, and it outputs something like 0.99. An almost certain yes. If the model calculates a score of -5, the sigmoid squashes it down to 0.01. An almost certain no. And what happens if the model calculates a score of exactly 0? The sigmoid function outputs exactly 0.5. A perfect 50-50 toss-up. This gives us our probability. So here is the big secret of logistic regression. It actually still has a linear regression model hiding inside it. It's a two-step process. Step 1. It takes your inputs like age, salary, etc., and uses a linear model, y equals mx plus b, to calculate a score. This score can be any number, just like before. Step 2. It takes that score and plugs it directly into the sigmoid function. The result? A perfectly clean probability between 0 and 1. That's it. It's just a linear model wrapped in a sigmoid function. Okay, but a probability of 80% is still not a final yes or no. We need to make a firm decision. To do that, we set a decision boundary, or a threshold. The default common sense threshold is simply 0.5. If the model outputs a probability greater than or equal to 0.5, we'll predict class 1. If the probability is less than 0.5, we'll predict class 0. It's that simple. 80% chance? We predict spam. 40% chance? We predict not spam. So let's look at our hours studied data again. Instead of that useless straight line, this is what the logistic regression model looks like. It's the S-curve fitted to our data. You can see for low study hours, the curve is near 0. For high study hours, the curve is near 1. And it crosses that zero point 0.5 threshold line right in the middle. This is a much better fit for our data. And this leads to a super important concept. The threshold is at 0 0.5 on the y-axis, probability, but the decision boundary is on the x-axis, our data. If we trace the 0 0.5 threshold over to our S-curve and then drop a line straight down, we find the exact x value where the model changes its mind. Let's say it's at 5 hours. This vertical line is our actual decision boundary. The model has learned a simple rule. If hours studied is less than 5, predict fail. If it's more than 5, predict pass. That's all the model is. That was with one feature, but what if we have two features, like age and salary, to predict if a customer will churn? Now our S-curve becomes an S-surface in 3D. But when we look at it from the top down, which is what this plot is, that 0 0.5 threshold becomes a straight line. This is the key. With one feature, the boundary is a point. With two features, the boundary is a line. With three, it's a plane. Logistic regression is a linear classifier. It finds a linear boundary to separate the data. So how does the model find the best S-curve? How does it learn the right boundary line? By exactly the same process we learned in B3. It starts with a random S-curve. It uses a cost function to measure how wrong that curve is, and it uses gradient descent to take downhill steps and slowly adjust the curve until it finds the one with the lowest possible cost. But there's one final important catch. We cannot use the same mean squared error cost function we used for linear regression. Why? The math is complex, but the intuition is simple. If you combine MSE with a sigmoid function, the error mountain isn't a nice smooth bowl anymore. It becomes a wavy, bumpy landscape with many little valleys. Gradient descent will get stuck in the first valley it finds, which isn't the lowest one. To fix this, we use a new cost function designed specifically for probabilities called log loss. All you need to know is that log loss creates a perfect smooth bowl again, so gradient descent is guaranteed to find the one best solution. And the intuition for log loss is really smart. It's a confidence penalty. Think about it. If the correct answer is spam 1, and our model predicts 0.9, 90% confident, it gets a tiny, tiny penalty. That's good. But if the model predicts 0.1, 10% chance, and is confidently wrong, log loss gives it a huge penalty. The cost shoots towards infinity. This forces the model to not just be correct, but to be confidently correct. It's a much better way to train a classification model. So let's recap. We learned why linear regression is the wrong tool for classification. We learned how logistic regression solves this by using the sigmoid function to squash outputs into a probability between 0 and 1. We learned how to use a decision boundary, like 0 0.5, to turn that probability into a final yes or no prediction. And we learned that this model is a linear classifier and that it learns using a special cost function called log loss. But this raises a new question. What happens when our data can't be separated by a single straight line? For that, we need a completely different and much more intuitive model. In the next video, we will cover decision trees. Subscribe so you don't miss it.